In today's discussion, we will see the languages, those are accepted by Turing machines, right? So these languages are called recursively enumerable languages, and we will see what is the meaning of enumeration, why the name is so, and we will again see some languages which are not actually recursively enumerable. Still those are being accepted by Turing machines, but the detail of those languages we will learn in the next lecture. And we will see one more concept, that whatever the transition of a Turing machine is doing for a particular form, so we can represent it in the form of binary strings. So you can means it is so essential that whenever we are able to represent the total transitions in a form of just binary string, so it is so much beneficial. We will be able to know in the later lecture series is that this binary representation is really so much helpful for us. Okay, so let us begin. Here, before beginning or before just entering to the process, we will just recapitulate what is a recursiveness. Okay, so here means recursive means it is a synonym of decidable. So here we are just concerning of those algorithms which are decidable and which are not. Means for a particular problem, whether the algorithm exists or not, means whether whether this problem can be solved, or whether the algorithm for this problem can be defined or not. So those problems for which we can define an algorithm are called decidable, and for which we are not are called undecidable problems. Fine. So we know that what a recursive is, what is a recursion, we have learned it. So we will see here how it is being used in case of this Turing machine. Fine. So this is a term recursively enumerable. It harks back to the same family of concepts. Means we will see that how it will be getting called repeatedly. Means whenever a function calls itself, we call that as a recursion. So here the same feature will be maintained. Here you will see that same thing is being called repeatedly for the purpose of execution, right? So we will see the same procedure to be followed here whenever we will define this recursively enumerable thing, right? So function could list all the members of a language in some order, that is, it could enumerate them. So what is the meaning of enumeration, right? How it is going to enumerate, we will see those in the next slide, right? Here, what is actually an enumerator is, the term enumerator originates from a type of Turing machine variant called this enumerator, right? So here one term is there called enumerator, which we will see how it is functioning. So then the concept will be clearer to you, that you will be able to know that okay, they say it is enumerating something, right? So here if you define this enumeration loosely, or if you define this enumeration process informally, it will be like an enumerator is a Turing machine with an attached printer. We will just means to logically define this one, how enumerators are working, what enumerators are. We will think of a Turing machine. Turing machine is what? Which can process a string of inputs. By placing on its step, it will have a header, right? So wherever it is going to point, it is going to process that input string. After processing, it will transit to different state, and all that we know that how a Turing machine works, right? So if we think of a Turing machine with the attached printer, it will be like a enumerator. How it will work? The Turing machine can use that printer as an output device to print strings. How it will be working? Say we are feeding one string or one input string to the Turing machine. Now it will do what? If it sends that input signal to the printer, means obviously that input string should be a accepted string, right? If it is not a accepted string, the Turing machine is not going to accept it. So whenever a string which the Turing machine is going to accept, if it gets that string, it will send it to the printer and the printer will print it, right? Means it will send it to the printer. Do not think that it is a real physical printer, it will get printed, not like that. We can logically map the concept like this. Now let us see how it looks like. If we have to mention or represent it schematically, it will be something like this. You can see that it is having a tape of zeros and ones, and how these zeros and ones are being generated we will learn in the later slides, right? So for now let us just assume a tape with 0 and 1. See, one finite control or control unit is pointing to a particular area, and the printer is printing the string whichever the Turing machine is processing. And the same thing can be depicted in a reverse manner. We will see a theorem on that. So here what it is doing, an enumerator E starts with a blank input tape. If the enumerator doesn't halt, it may print an infinite list of strings. So you will see in the next lecture that this is a drawback of Turing machine. In some cases the situation may be like this, that the Turing machine cannot for a particular string, so the Turing machine is not able to move to a accepted state, right? So in that case what will happen, the Turing machine keeps on processing, and it will never halt, right? So there are some situations arises. So if this is the situation that the enumerator doesn't halt, it will keep on printing, right? So the processing will be continued. This is what we want to focus here, right? The language enumerated by E is a collection of all the strings that it eventually prints out. Moreover, E may generate the strings of the language in any order, possibly with repetitions. So how it will generate in any order? Say we have seen some in any kind of scenario. So the Turing machine may move right, Turing machine may move left according to the transition functions which we are developing. So here there is no hard and fast rule, okay, you have to follow this fashion to enumerate the string, right? So it can process in any manner, in whichever our processor needs for now, right? In whichever manner we want to process the string for now, that will be followed, nothing else. Now let us see what next. Here we will focus on a theorem. What it is saying, that a language is Turing recognizable if and only if some enumerator enumerates it. That means if we say in other language, a Turing machine will accept those language which are recursively enumerable languages, right? That means a language which can be enumerated by some enumerators. That means what? Those languages are recursively enumerable language, right? And you have seen here that it is a continuous, or it is a process where, say this one thing is being done, it has this string has been processed, it is going to get to the printer. Again that input, that process, whatever wherever we have gone for a particular transition, that is going to call for the second go, right? The second transition will be followed from the first, third will be followed from the second, and so on. That's why it's a recursive process, right? So here if this kind of languages are there, that language is going to get accepted by Turing machine. So how we are going to prove this one, right? First we will show that if we have an enumerated E that enumerates a language, say A TM, that is Turing machine M, recognizes E. So if this is the scenario, say enumerator, we at firstly we are giving a language A to the enumerator E, and it can enumerate that language, right? And if my Turing machine M can recognize that language A, so how it is going to work? Fine. Let us say we're having an input string W. So how it is going to process? So we will run that W on enumerator first, since in this procedure we are beginning with the enumerator, and dictating the Turing machine, okay, you just enumerate those strings which the enumerator is enumerating, or you just process those strings which enumerator is enumerating. So firstly, we are going to feed this input string to the enumerated E, right? So every time E outputs a string, compare with W, right? So enumerator is enumerating a string, and obviously it is going to compare with the input string which my Turing machine is going to follow. Otherwise it will come up with a different strings which my Turing machine is not going to accept. So it needs this comparison. So if W ever appears in the output of E, it will accept, right? So whatever my enumerator is enumerating, if W is a part of that enumeration, or if it is it got enumerated, that W part, then it will be accepted, right? Now clearly we can see that M accepts those strings that appears on E's list, right? So in E's list we are continuously doing what? E is enumerating something, we are continuously comparing it with W. So it is very easy to understand that fine, E is going to accept only those things which are present in W, right? Done. Now M is doing what? M is going to accept W. So M is accepting which strings? The strings which are appear on E's list, that is enumerator's list, right? Now if we follow the reverse process, means what? If TMM recognizes a language A, we can construct the following enumerated E for A. So in the previous case, what we did, we followed the enumerator. Okay, enumerator is processing in the fashion, enumerator is enumerating a string, it is comparing with W, then E was that W was being accepted by M. So the same thing, means E ultimately M is accepting those strings which are in enumerator's list. But here what we will do, here firstly we are assuming that my TM is recognizing a language A. So based on this acceptance, or based on this recognition, we are going to construct the enumerated E for the language A. Now let us assume we have this possible set of strings which are part of input alphabet. Fine. What are those strings? S1, S2, S3, anything, right? So if E ignore the input, E is not means following any input, it will just follow the set of strings, right? So what we are going to do, we will just input a loop. Here I will run from 1 to whatever the end is, say end symbol, say fine I or J or whatever the steps it is going to follow. Then it will be a repetitive process where it will run for the, means the Turing machine name will run for ith steps by processing all the strings, say S1, S2 followed by Si, right? Now if M accepts a particular string S, eventually it will appear on the list generated by E. Fine. So since E is enumerating those strings that my Turing machine is recognizing, so ultimately what is the scenario? Again here M is going to accept those strings, and that will be obviously in the list of the enumerator which it has enumerated, right? In fact it will appear on the list infinitely many times, because M runs from beginning on each string for each repetition of step 1. That means what? Say one string, say S1, say it is having a length of say 10, right? S2 having a length of 10, S3 having a length of 10. Say if this is the situation, so for each and every loop, or each or every repetitive process, my M will run from 1 to 10 for S1, for 1 to 10 for S2, and this fashion. So it will keep on repeating itself unless and until all the strings got processed, right? And we can, since we have learned of the concept of multi-step Turing machine, we can do what? We can just parallelize this process. It will do what? It will have different tapes, say dedicated, each tape is dedicated for each string, so we can do there will be say I number of strings are there, so there will be I number of finite control pointer, so it can do it. Again we can, and same thing we can we can just simulate that multi-tape Turing machine to a single tape Turing machine. We are means quite means you know how to do it, right? So we can follow that process as well. Fine. So now it is quite understandable now that we have learned the languages which can be placed or which can be represented in the form of enumeration, or those languages are called recursively enumerable languages. Fine. So we have seen that the Turing machine can accept those language. Now if the situation is like this, if a language, there are some languages that are not recursively enumerable, fine, so those languages are called recursive or decidable language. We will follow the means we will learn the details of it in our next lecture. For now just know the terms, the languages, those are being accepted by Turing machine, but you cannot enumerate those language, right? So those class of languages are recursive or decidable language. We will follow in the next lecture series. Now for now we will learn one very important topic. Just see here, if undecidable language consisting of a pair of like this m comma w, right? So m is for here is a Turing machine, and w will always be a string of zeros and ones, and m accepts w. So if we can express any Turing machine or express any language in this form, the machine followed by the string, and whatever the string we are writing, that will be a binary string. It will consist of only zeros and ones, and the fact is that okay, this Turing machine will accept this form of language, this form of strings, right? So how to generate this w, we will see that one, that how we are going to binary code it. And if this problem with inputs restricted to the binary alphabet is undecidable, then surely the more general problem where Turing machine may have any alphabet is undecidable. Can you see the beauty here? So if we can represent the total working principle in the form of just zeros and ones, that okay, my this is going to, this string is going to, or for this combination, this Turing machine and this input pair, this alphabet is undecidable, right? So we cannot decide it, that whether the program will halt or the Turing machine will halt. That means then for the particular problem whether the algorithm exists or not, that if we can define or if we can decide by just using two input alphabet, that is 0 and 1, and can conclude that okay, if it cannot work for it, it will not work for any input alphabet, so it can be done so easily, right? So we will see how to represent it in the form of zeros and ones, right? So let us just move directly to there, how to enumerate the binary strings. So here just we will see the procedure. Whenever we will move to the total code for Turing machine, the concept will be clear. We will see an example and the concept will be clear, right? Say we are having a binary string w, we will treat one w as a binary integer I. Okay, we will see why one w and all. We will see in the next procedure which we are going to follow. Just for now, remember this thing. For the first string, we will use epsilon. That means no zeros and no ones are there. For the second, we will represent it as 0. For the third, we will represent it as 1. It's just a binary pattern, right? Then 2 bits form will come, then 3 bits will come, and this it is going to follow the same fashion, right? So it is following a lexicographical order. You can see that it is based on the length of the strings, right? So let us directly move to the codes for Turing machine. This is more important. What we are going to do, say we are having one Turing machine, this one M, where the states are Q, and it is a set, it may be a set of states. We are not representing it, means total set is say capital Q. Then input alphabets will be obviously 0 and 1. The tape alphabets are there, transition functions, starting state then blank symbol and final states, everything are same as we use to represent a Turing machine, right? So we will see how it works. Now here we are assuming the states are in this fashion. Remember, here we are using q1 to qr. Initial state is q1 and we can use anything, right? So there are total r states, so it is ranging from q1 to qr, and the start state will always be q1 and q2 will be the only accepting state. Here just see, we will reduce the total form in just two states, right? Why? Because we may assume that Tm halts whenever it enters an accepting state. That is never any need for more than one accepting state, right? Here, if you remember, we are just using 0 and 1 to represent everything. So my two states will be enough for it, right? We can represent the total transition just in this form, q1 and q2. We will see that whatever the state number of states are appearing in the total Turing machine part, whatever Turing machine we are going to represent it in using the binary strings, so we will see that can be done using just 0 and 1. Okay, now here type symbols will be like this. X1 will always be the type symbol 0, x2 will be 1, and x3 will be blank b. Just these are the conditions we have to follow. Here we are going to use d1 to denote the left direction and d2 to denote the right direction. Fine. Now see, we have to remember this, that how we are going to do. Suppose a transition is there where delta of qi comma xj is I should be in suffix. Okay, there is some typos here, just correct it off. Q suffix I, and it is transiting to qk and replacing xj with xl, and then direction is dm. Fine. So if this is the situation, right, and ijklm are some integers. Okay, we will see how to represent those in the form of integers. Why this will be integers? Say we will use the state like q1, q2, q3, q4, q5, like this, right? So I will be some value of 1, 2, 3 or something like that. Similarly for x variable, we will use what? We will use 1, 2, 3, anything. So x1 will be replaced by say x2 in this fashion. So it will be integers, right? And dm will be either 1 or 2, since we are using d1, that is to denote the left, and d2 to denote the right. So what is the rule to code this one? 0 to the power I, 1, 0 to the power j. See, alternating 0 and 1s are there. Only 0 is having this powers of whatever qi, qj, all those integers will be raised to the power of 0, and 1 is acting as the separator here, right? So this is, if you say ask why this is the form, this is the way in which the algorithm was defined to code the Turing machine. We have to follow the steps, right? These are being proven steps. Okay, if we can represent the Turing machine using this form of coding, so we have to follow this one. Okay, so for a particular code we have seen how to do it. Now here between two different codes, say C1 is one code. Why C1 is one code? Because say for one transition, delta q1 comma x1 is transiting to say q2 comma x2 comma say d1, right? So this is one code. Say this is C1. Similarly, there will be one more transition function, that will be C2, another more C3. So between these two we will use double one to separate between the two different codes, so that whenever we are having just that code, we have to develop the Turing machine from it, so we can develop it easily. Okay, now let us directly move to the example. I think it will be better. So this is my Turing machine given, right? So these are the transition functions, right? q1 comma 1, q3 0 are in this way. Just remember what we have used. x1 stands for 0, x2 stands for 1, and x3 stands for blank. So we have to replace the values like this. Say we want to just see with this one, just the first transition, what it is saying, delta of q1 comma 1 means x2, that means delta of q1 comma x2 is equals to q3, 0 means x1, that means q3 comma x3 comma r means what, d2, right? So if this is the fashion, just see, we have used this function and we have replaced 1 with x2, 0 with x1 and r with d2. If this is the form, then how the code will be? If you remember the code was like 0 to the power I 1, 0 to the power j 1, 0 to the power k, in this fashion, right? So here I means what? What is the I? What is there in the suffix of q, this delta followed q by q, right? Whatever, what is the suffix of it? It is 1, means delta of within bracket there is q1 comma x2, so i's value is 1, j's value is what is there in the suffix of first x, that is 2, so j's value is 2. And if we proceed to the right hand side, then k's value is what, 3, right? L's value is what, 1, and then n's value is 2, right? So you can you follow the fashion? So it will be, the first code will be 0 to the power 1, 1 to 1, 0 to the power 2, in this fashion, right? So if you code this one, so it will be like what, it is the first line of the slide, there is 0 1 0 0 1 0 0 1 0 1 0 0, fine. If you again now it just try of your own, if you follow the second transition property or to second transition, whatever it is given there, it will find the second one, the code will be like the second one. For the third it is like the third, and the fourth it is in the fourth here. Now what we have to do, we have to combine all the 4 codes. How we are going to combine it? The first line here, 0 1 0 0 1 0 0 1 0 1 0 0, then 1 1, right? Then the second line, that is 0 0 1 0 1 0 1 0 0 1 0 0, then again 1 1, then the third line, then again 1 1, then the fourth line. So if you combine the total code in this fashion, it will be somewhat like this. Okay, now why we have written this code? The pattern may be different. Here we have written the first code first, then 1 1, then second code, then 1 1, the third code 1 1, then fourth code. We can arrange it in any of the possible, whatever choices we can. Okay, whatever the way my Turing machine is processing, we can follow that fashion. We can write the fourth code first, we can then second, then say first, then third. So in this fashion, if you arrange and rearrange it, it is what, it will be 4 factorial. We can combine on, we can permute in this manner, right? So it is 4 factorial, so there will be 24 codes for this machine, fine. So if there were 5 codes, how many codes were there? 5 factorial, right? If there are 2 codes, there will be 2 factorial ways of representing it, fine. So in the next class we are going to learn another language, that is recursive language, and we will see how it differs from the recursively enumerable language. Thank you.